Okay, so this one is what we had taken as an example of what we call inverse proportion, or an inverse relationship. When one number gets larger, the other gets smaller. In this case, it's the number of teeth. Here, the number of teeth gets smaller. Oops, the number of teeth gets smaller. The RPM is going to have to get larger. So this number here has to be bigger than 60. We don't use a proportion for this. We use a product instead of a ratio. Number of teeth times its RPMs, 48 times 60, has to equal number of teeth times its RPMs, 32 times X. Now we're going to multiply 48 times 60 divided by 32, which should be 90 equals X. How many of you had 90? Do you see what you did? You did 48 over 60 and did it that way. That would be assuming it's directly related. Remember, that's always the first question you have to ask. Is this direct relation? Do the two numbers get bigger together, or is it inversely related, where one gets bigger, the other has to get smaller? The gear with the fewer teeth has to turn faster. So it's inversely related. Okay, when you guys left here, you guys had just a few problems out of your packet. Do anybody have any questions on those? Or is it 41 through 45 or something like that? Yeah, all three problems. You guys doing well? Okay. Well then, so what we've been kind of talking about is this relationship between sides of similar figures. If you blow one figure up, how you can find those missing sides. This even applies to three-dimensional figures. Let's see. Do I have one on here? There we go. We're going to make this easier on myself. Gee, thanks. You're supposed to say, oh, that's almost as pretty as yours. Yeah, see, mine's wireframe, so you can see through it. Now you're getting the picture. You're supposed to suck up. Okay. So now, this one, let's say this is an enlargement. The bigger cylinder is an enlargement of the smaller one. So this is 12 inches tall and 9 inches in diameter. This is 20 inches tall. What would its diameter be? Well, these are just lengths. So our ratio of lengths, 12 to 20, is what? 12 over 20. It would be 9 over x. Cross multiply and divide, you get 15. So this diameter has to be 15 inches. Those units stay the same. Just like our similar two-dimensional figures that we talked about yesterday. Well, what if we're not measuring a length? Let's see what I mean by that. What if I have something like this? I'm going to take this rectangle here. It's 2 inches by 5 inches. Now I'm going to blow it up. And make it now 6 inches here. First, what does this dimension have to be? 15. Good. We could have set up that proportion if we wanted to. We have 2 became 6, so 5 becomes x. We cross multiply and divide. We're going to get 15. What I'm most interested in here, though, is what is the area of this one? 10 inches squared, right? What's the area of this one? 90 inches squared. So if I look at my lengths, that ratio of lengths was 2 to 6, or reduced to 1 to 3. However, when I look at my area, my ratio of area was 10 to 90. The square inches will cancel out, or a 1 to 9. Not the same ratio, are they? So the question becomes, if we blow up a figure, if we know the ratio of the sides, do we know the ratio of the areas? Well, let's look at another example. Let's take a square. Let's say this square is 3 millimeters on a side. And we're going to blow it up, and no, this is not going to be drawn to scale. I'm going to blow this up to 12 millimeters on a side. What's my ratio of areas? Well, 3 to 12, which reduces to 1 to 4. Right? Not areas, sorry. Not areas. What am I talking about there? Lengths. My ratio of lengths is 3 to 12, or 1 to 4. My ratio of area, well, what's the area on this first one? 3 by 3, or 9 millimeters squared. What's the area on this one? 12 by 12, or 144 millimeters squared. So the ratio of areas is 9 to 144, which reduces to a 116. Again, not the same, but is there a relationship between them? Now look up here. 1/3 ratio of lengths gave a 1 to 9 ratio of areas. Yeah, well, it's squared period. 1 squared is 1, 3 squared is 9. Here, 1 squared is 1, 4 squared is 16. Yeah, actually it will be when we get there, yes. We're going to get there next. So if I have a figure, let's say I have a really unusual, irregular figure, it looks something like this. And I enlarge it. That. And let's say that I know that this side here was 6 inches in the original figure, and it's now 15 inches in this figure. This area here was 100 square inches. What's this area here going to be? Well, again, we're going to start out with the ratio of lengths. Ratio of lengths is 6 to 15. Now, I don't have to do this, but it's so much easier if I reduce it. What's that reduce to? 2 to 5, right? Now, when I go to talk about the ratio of areas, I have to adjust this. I'm going to have to square it. 2 squared is 4. 5 squared, 25. So my ratio of areas is going to have to be 4 to 25. Where does the 100 go? Came from with the 6, right? 6 is on top, so 100 goes on top. So cross multiply and divide, we're going to get 625 here. So that is an area of 625. What do you think? Yeah, better than a sharp stick in the eye? No, I'm not coming up with a new one. Done that a couple times. Okay. Give you something to compare to. Oh, cool. Let's say that this here is 4 inches on the side. And this here is going to go to, let's take it up to 14 inches on the side. Again, not drawn to scale. But these aren't cubes. They're irregular, they're just boxes. But this one is an enlargement of this one. But I'm going to tell you this, the surface area here is 120 inches squared. What's the surface area of this one have to equal? Well, even though these are three-dimensional objects, this is still an area. So the ratio of my lengths is 4:14, which will reduce to 2:7. So now when I go to look at areas, what do I want to do again? Square that. So what's that going to give us? Yeah, 2 squared is 4, 7 squared is over 49. Then, of course, the 120 has to go on top. And we shall cross multiply and divide. 49 times 120 divided by 4 is what? 1470 inches squared. Good stuff. What's that? Looks more like a peanut to me, but so let's say for this first one here, and this isn't in reduction now, it's been shrunk. Let's say the surface area of this first one here is 900 square inches. In your notes, try to find the surface area of that second one quick. Oops. So, what's our ratio of lengths? 12/5. Not much we can do to adjust that, is there? So then our ratio of areas becomes 144/25. And then 900 goes on top. Cross multiply and divide, we get 6.25 square inches. Not so bad? Okay, you already brought this up. You guys figured this one out ahead of me. So we can just jump right to it. So we're going to look at just a simple box here. And let's say that this side here is 3 inches, 7 inches, and 4 inches. And I'll make this one 8 inches, 14 inches, and 6 inches. There's my ratio of lengths. Well, 6 and 3 go together, don't they? So 6 to 3 reduces to a 2-to-1 ratio. What'd you guess must happen if we go for look for the ratio of volumes? Well, somebody predicted you'd cube it, right? Here's the power of the number of dimensions. Yes, volume is 3 dimensions, so it's going to be the third power. 2 to the third power is 8. 1 to the third power is 1. Well, let's check this out. What is the volume of this? 6 times 14 times 8 is 672 is correct. Inches cubed The volume of this, 3 times 7 times 4, 84. So is 672 over 84, does that divide out to be 8 to 1? Sure does. Okay.
So is that some concept of drawing from squaring to your ranges and power of the dimensions when you get into like higher level maths or adding in?
Oh yeah, if you get in multi-dimension theory, so you get the 4th and 5th dimensions and stuff like that, yes.
Like mass density too, if you're going to do that?
Density does not change when you enlarge, unless you're enlarging on a molecular scale and you're expanding the distance between the particles to enlarge. Then the density actually decreases as you enlarge, so that's an inverse relationship, so that would work differently. But mass will increase. Mass is generally a 3-dimensional thing, so it'll increase as a cube of the length. So it all depends on what dimension that quantity is related to. Mass is related to volume. Well, mass is related to volume and density, and since the density is not related to size, its mass is just strictly related to volume. So it goes up as a cube. There are other things like inertia and kinetic energy and stuff like that that are the same way. So let's say I have an irregular shape. Don't ask me what these shapes are supposed to be. I don't know. I just draw them. And not very well at that. Let's say that this here is 12 inches and this is now 20 inches. And this volume here is 600 cubic inches. What does this volume here have to be? In your notes, try to figure that out for me quick. So, ratio of lengths. What's the ratio of lengths here? 12 to 20. I'm going to reduce that by 40 to 3 to 5. Divide it by 4. Reduce it by 4. So that means my ratio of volume is going to be cubed. 3 cubed is 7, 5 cubed, 125. 600 has to go to 125. You don't have to reduce it, you're just going to end up with like, what, 1728 over 8. Yeah, 1728 over 8,000. That's a little bit big numbers, but it still works. Cross multiply and divide, we get what? What's that? 129.6 inches cubed. Yeah, you'll get the same answer, just got bigger, uglier numbers is all. Okay, well, to practice this, I'm going to give you a little bit more work time today since I've been cutting you short. I'm going to give you a worksheet. And on that worksheet, it's going to be problems 1 through 16. All. No odds on this. This will be a new worksheet that I'll hand out. We're going to still get back into that other packet, but this is just a newer worksheet that I'm going to hand out for today.